Hi, I'm Andreas, and welcome to this presentation for Lutsig, a verified Verilog compiler for verified circuit development. Let's start by summarizing what is going on here. So first, it is good to know that Verilog is the most widely used hardware description language today. And what we have done is that we have built a new verified Verilog compiler called Lutsig. And Lutsig targets a class of FPGAs, that is, programmable logic, and specifically, Lutsig is capable of producing technology map netlists for FPGAs. And in the paper and in this presentation, we show how to use Lutsig in verified circuit development. And lastly, all of this has been done inside the interactive theorem prover Hall 4. The outline of the talk is as follows. First, I will say something about how we suggest using Lutsig for hardware development. And then I will mention some interesting details about the internals of Lutsig, and finally we will conclude. So let's start by saying something about hardware development using Lutsig. The approach that we follow here is essentially that we try to mimic what is usually done when developing verified software inside an ITP, but we do it for hardware instead. So let's start by recalling what is usually done when developing verified software inside an ITP. So we start with some program, for example an SML program, and we have a verified compiler, for example the KML compiler. And then we want to produce machine code for some target machine, for example machine code for x86. And this is of course done using the compiler. And since we want to develop verified software, we need to get a theorem from somewhere, a correctness theorem. And this is usually done on the source level. So we produce by some means a source level correctness theorem for our program. And we do this on the source level because it's easier to reason on the source level than on the target level. However, ultimately we are interested in the correctness of the target level program because this is what will ultimately be run on our target machine. So we get a target level correctness theorem by simply composing the source level correctness theorem with the correctness theorem of our compiler. And in this way we get target level correctness theorem without having to reason about target level constructs and so on. So this is convenient. And if all of this is done inside one single ITP, we end up with a very small trusted computing base. Specifically, the trusted computing base will consist of only the correctness specification used in the program correctness theorem, and the target level semantics, and the theorem prover itself. And to mention some things not included in the trusted computing base. For example, the source semantics is not included, and the compiler is not included, and no other intermediate completion steps are included either. So quite small trusted computing base. But that's the story for software. What about hardware? So instead of a software program, we have some hardware design or hardware program, for example a Verilog program. And instead of wanting to produce machine code, we want to produce some kind of hardware, for example netlists for FPGAs. And instead of a software compiler, we have a hardware compiler. But when you start looking for one of these hardware compilers, specifically verified hardware compilers, you will quickly realize that the software compilers in the context of verification have received a lot more attention. And as far as I know, there are essentially just two previously verified hardware compilers. The first one being a compiler for a BlueSpec inspired language from a few years ago, and more recently there's another verified compiler for another BlueSpec inspired language. And now since this paper there is also Lutsig, but instead of compiling from a BlueSpec inspired language, we compile from the most used hardware description language, that is Verilog. And we also do technology mapping, which is not done in these previous compilers. So that's something that is new with Lutsig. And Following this approach that we usually follow in software development, we produce our correctness theorems on the source level. And to do this, we use previous work. So we use a proof-producing translator from shallowly embedded Verilog circuits to deeply embedded Verilog circuits. And this allows us to prove theorems using shallowly embedded Verilog circuits, and then using this translator, port these to deeply embedded Verilog circuits that can be used as input for Lutsig. And this proof-producing translator was simple to connect to Lutsig, because Lutzig's Verilog semantics is built upon the semantics used in the proof-producing translator. Okay, but that's the context. Let's actually look into Lutsig itself, the compiler that we have developed here. So what about Lutsig then? Here to the left we see an example of the kind of Verilog code Lutsig accepts as input, just in case you haven't seen Verilog code before. And to the right we see one FPGA board you might want to target. But on this abstraction level we don't really get a lot of information when we look at this FPGA board, so let's zoom in a bit. So let's zoom into the FPGA chip on the FPGA board. So here we see a visualization of a compilation result of a Verilog program. And we can zoom in a bit more. So here we see that essentially the same structure is repeated over and over again. So let's zoom in a little bit more. And now when we have reached this level, we see what kind of hardware resources are available to us when we target FPGAs. So we have lookup tables, so-called LUTs, that can be used to implement combinational logic. And we also have registers that can be used to hold state between clock cycles. So that's some of the resources that we have available. But let's not get stuck in details here, and let's go back up again. So zooming back up to this level, we can now ask what do we need to do to go from the kind of Verilog code you see on the left hand side here to FPGAs. So one usually says something like this when describing this process, that we start with Verilog code, and then we do some kind of compilation or synthesis to netlists. And these netlists need to be technology mapped for the technology that we target. Here we target FPGAs. And these technology mapped netlists need to be placed and routed for the FPGA chip that we target. And this new netlist need to be encoded into a format that the FPGA will understand. And this is usually called FPGA bit streams. And these FPGA bit streams can be loaded onto the FPGA board that we're interested in. And the steps covered by Lutsig are the ones inside this yellow box. So Lutsig covers compilation or synthesis and technology mapping. And we did not include the placement and routing because the approach we take to technology mapping we expect to be applicable to placement and routing as well. Since everything inside the yellow box is done formally, we need a formal semantics for our source language, that is Verilog, and also formal semantics for our target language, that is technology mapped netlists. So let's look into those two semantics. So for Verilog, so as previously mentioned, our Verilog semantics is based on previous work. And the semantics is a functional operational semantics, and the semantics is supposed to be a sound simplification of the latest Verilog standard. And the development process for the semantics was essentially that I read the standard, and then I sanity checked my understanding using secondary sources and simulator experiments. And then this process was repeated over and over again. But we should keep in mind that the Verilog semantics is not part of the TCB of circuits developed using Lutsig, or more specifically, Verilog circuits developed using the development methodology outlined in the beginning of this talk. But we still need something reasonably close to Verilog to be able to call Lutsig a Verilog compiler. And if you're familiar with the Verilog standard, you know it's an enormous standard. And indeed, Lutsig only supports a subset of Verilog. And let's describe this subset here. So the top-level construct of the kind of Verilog Lutsig support is a module. And these modules declare some inputs and outputs and takes a clock input, because as we target FPGAs, we are interested in synchronous circuits. And then the contents of these modules are essentially lists of always blocks. And the contents of these always blocks are mostly standard imperative language constructs, a kind of C-looking programs. Okay, so that's the source language. What about our target language? So it's natural to visualize circuits as graphs, as you see here to the right. But in functional programming and proofs, it's easier to work with circuits represented in some linear fashion. So that's what we did here when working with Lutsig. So our netlist language is a simple custom netlist language that can be easily pretty printed for communication with PNR tools. So it's supposed to be an unexciting netlist language that you can simply pretty print when you need to pretty print it. And formally, the situation is as follows. So as with the Verilog semantics, our netlist language or netlist semantics is a function operational semantics, and it's essentially an assembly language without jumps, so everything runs each clock cycle. And this example here illustrates some of the things you can do with the netlist language. So you can declare initial values for registers, and then in most netlists there is a long list of cells or gates and information about how these are connected, and then also information about how the registers should be updated each clock cycle. Okay, so that's something about the source and target language of Lutsig. What about Lutsig itself? So there are 4 important passes in Lutsig. So the Verilog to netlist compiler, and then X-optimization pass, and also technology mapping for high-level cells, and then technology mapping for the remaining cells. So let's go over them one by one. So the compilation to netlists. So for the compilation algorithm, it is based on the unverified Verilog compiler CSyn. And if you're familiar with software compilers, you will recognize many parts here. For example, compiling expressions is quite straightforward. So if you look at this example of compiling addition, it will look quite familiar if you're familiar with software compilation. So we simply recursively invoke the expression compiler twice, and then we merge the result from the recursive compilation calls with the new cell. So many expressions are simple like this. So expressions are quite straightforward. But what about statements? So statements are a little more interesting. And the high-level picture is essentially that each Verilog variable is compiled to a register, and then we need to build a next state netlist for each register. So this netlist will be, or netlists will be inferred from assignments and if statements and so on. And one interesting aspect of Verilog is that we have 2 different kinds of assignments actually. So blocking assignments and non-blocking assignments. And here we see a program containing only blocking assignments. And in full Verilog, always blocks are interleaved non-deterministically when they are executed. So in this case, as blocking assignments is essentially the kind of standard assignment you're familiar with from standard imperative languages. Here we will not know what we will read when we read A when we update B, because we do not know if the first or second always block will execute first. So this is where non-blocking assignments come in, because if we use a non-blocking assignment in the first always block, then we will always read the previous value of A in the second always block. So non-blocking assignments are useful for communication between always blocks. And in the formal semantics, non-blocking and blocking assignments are handled by keeping track of two variable environments, and these environments are merged at the end of each clock cycle. And we can also think about a concrete example how we compile a simple Verilog program to a netlist. So remember that in the semantics we have two environments for variables, one to keep track of blocking assignments and one to keep track of non-blocking assignments. And it's similar in the compiler. So we have one map to keep track of the blocking assignments and one map to keep track of non-blocking assignments. So when we go through this program here, we will see that the maps are updated. So after having compiled the first line, we see that the non-blocking sigma map has been updated, saying that A is now equal to 3. And we did not need to generate any new cells here. But for the second line, the right-hand side is more complicated, so we need to generate new addition cells. And after we have done that, we also need to update the sigma for B to say that if we want to read the value of B, we should look at wire W1, which is the output of one of these new addition cells. And what about if we have if statements in our always block? What do we do then? So we first compile both branches such that we get two new netlists and updated sigma maps. And then to merge all of this, we simply do as follows. So for the netlist, we simply concatenate the two netlists and then generate some new max cells to merge the results from the different branches. So for example, we see here that A is assigned in both branches. So in the true branch it's assigned 3, and in the false branch it's assigned 0. And we see this reflected here in this sigma map here, saying that in the true branch A is 3, and in the false branch A is 0. And this is merged here, so this is from the true branch and from the false branch. And then this is the condition from the if statement. And afterwards, when we look up A in this sigma map for non-blocking assignments, we see that we point to this new max here. And one interesting aspect of compiling to netlists is that this compilation scheme might turn dead code into code that actually run. So consider a case where C is always true. Then it doesn't matter what happens in the false branch, because this will never execute in the Verilog semantics. But after having compiled it like this to a netlist and then simply concatenated it to the resulting netlist, this means that this netlist will actually execute each clock cycle. So it's not enough to make sure that there are no problems with respect to the dynamics and semantics here. We also need to make sure that the program is well typed, otherwise we might generate a nonsense netlist. So this is one thing to have in mind. Another important pass in Lutsig is the X-value optimization pass. So X-values relate to a larger problem in Verilog development, the so-called simulation and synthesis mismatches, meaning that your synthesized design might not have the same behavior as you saw in the simulation before you synthesized your design. So for non-verified compilers, if you do not follow specific coding guidelines, you may end up with such mismatches. But as Lutsig is semantics preserving, we know that this is not a problem for Lutsig. But to be actually able to prove this, we need Verilog semantics that make sense for hardware. So let's look into X-values. So X-values in synthesis is a way for hardware designers to signal don't care, meaning that the synthesizer is allowed to replace any X-value with any concrete value. And this is a way synthesizers can optimize the design they are given. So for example, consider this Verilog program to the left here. Here we have one X assignment here in the false branch. And if the synthesizer would replace this X value with 3, we could replace this whole if branch with just an assignment saying that A is equal to 3. And that would allow us to not generate any max for this if branch, if statement, which is quite nice. But one problem is that the X-value semantics in the Verilog standard is not a good fit for synthesis. So the Verilog standard suggests that bits should be able to have 3 different values, 0, 1 and X, and also Z, which is not relevant here. But if we allow bits to have the actual value X, it opens up various questions. So for example, this program here, if we assign X to C, what happens if we branch on C? Should we assign 1 here to A or 0, or should something else happen? And the Verilog standard says that we should assign 0 here, which is quite strange. So according to the Verilog standard, A should always be 0 after having executed this fragment. And this is not a good fit for synthesis. So we had to come up with a better semantics that makes sense for synthesis for X-values. And in Lutzig's Verilog semantics, bits can only take on the standard values, meaning being 0 and 1. And X-value assignments are given semantics by a stream of non-deterministic bits. So instead of having a symbolic representation of X-values, we overwrite old values with non-deterministic bits. So this is nice in some respects, but it also complicates Lutzig's correctness theorem a bit, because now we must say that for any run of a generated netlist, there exists a stream of non-deterministic bits such that the input Verilog program has the same behavior as the netlist. Or more concisely, that the output netlist behavior is a subset of the input Verilog program behavior. But all in all, this works out in the end. And we also use this semantics in the optimization pass. And we do this optimization pass on the netlist level. And the pass is carried out in 2 stages. So first we go through the netlist to find good replacement values, such that we can optimize away maxes, for example. And then we do a second pass when we do the actual replacement and remove redundant cells. And this is not only an optimization pass, this is actually a required pass, because our target cell set does not have any non-deterministic cells. So we actually need to replace all x values even if we do not have a good replacement value. So for those x values where we didn't really find a good replacement value, we simply replace them with 0 such that the netlist is deterministic after this pass. So we can later technology map it. Another important task carried out by Lutsig is technology mapping. Technology mapping in Lutsig is split into 2 passes, one pass for high-level cells and one pass for the remaining cells. We first look into the mapping of high-level cells. So technology mapping is when you take a netlist implemented in terms of abstract cells and produce an equivalent netlist implemented in terms of the cells natively available in your target technology, in our case FPGAs. So when targeting FPGAs, we could in theory map all cells to LUTs, but it's better to exploit all the special purpose hardware resources available to us. Remember when we zoomed in into the FPGA chip previously? Then we noted that we had, for example, LUTs available. But if we look closer, we also see other kinds of hardware resources, specifically carrier chains. And when mapping various high-level cells, such as, for example, addition or equality checks, then it's important that we take these resources into consideration. So when mapping, for example, addition, we template expand all addition operations into predefined networks of cells natively available on FPGAs. And when proving Lutsig correct, we need to also prove this mapping correct. But it's quite straightforward because we can do this mapping cell by cell. And the second responsibility of the first technology mapping pass is to pre-process the netlist for the second technology mapping pass. And this pre-processing consists of splitting array cells into networks of Boolean cells and also splitting array registers into Boolean registers. And finally, we look into the second technology mapper pass. The responsibility of the second technology mapping pass is to map all cells not mapped by the first mapper. And the second technology mapping pass stands out among the various passes in Lutsig because it is not verified. Instead, it is based on translation validation, also known as formal equivalence checking. Here, this means that we use a SAT solver to prove the input and the output of the mapper equivalent for each run of the mapper, instead of proving the mapper correct once and for all. However, note that because of the SAT machinery available in Hall 4, we do not need to add the SAT solver used to our TCB, because we still find a Hall proof for the equivalence claim, thanks to the Hall 4 machinery. So, the mapper is based on graph covering in the following sense. So first, we find a covering. For example, something like this. And each cover here is turned into a LUT. And then the second phase starts. Now we need to prove the input netlist equivalent to the output netlist consisting of our new LUTs. And this is where SAT solving comes in. So using Hall 4 automation, we break down the equivalence problem into a series of small Boolean problems that can be solved by SAT solving. And then, using more Hall 4 automation, we glue the results from SAT solving into a claim that the two netlists are equivalent. And we use translation validation here instead of verification because finding a graph cover is computationally expensive, and using translation validation allows us to run the graph covering search outside our logic instead of inside it. And for this first version of Lutsig, we use a simple placeholder mapper instead of utilizing an existing good mapper, because it was simpler to write our own mapper than integrating an existing one. We have now reached the end of this talk, so let's conclude. So in this presentation I have not given you a lot of details, but you will find more details in the paper, and in particular you will find 2 case studies. One case study is about verifying a simple moving average filter using Lutsig, showing how to use Lutsig in practice. And in this case study you will find examples of how we express circuits in whole, etc. And since Verilog is a popular language, it's possible to connect up Lutsig to other Verilog-based tools. And we have, for example, connected up Lutsig to the verified high-level synthesizer Verisert. However, Verisert is verified in COC, so we do not have a formal connection. But even without a formal connection, we see that Lutsig is capable of compiling the Verilog output of Verisert, showing the usefulness of Lutsig. All in all, we should remember that Lutsig is a new verified Verilog compiler that compiles Verilog designs to netlists and does technology mapping for FPGAs. Verified here means that Lutsig is proved semantics preserving, enabling us to transport properties proved at the Verilog level down to the netlist level.